So this is the introduction and the directions and some helpful tips for Lab 6, the ionic and covalent bonds. My first advice to you is to read the introduction before you start and read the procedure carefully because it will help you with some of the questions you might have. The second thing I want to point out is that there are puzzle pieces that are with this lab. You are not required to use those puzzle pieces. Personally, I've found the puzzle pieces with the ionic compounds are helpful for a lot of students, but the ones with the covalent compounds, those are the squared edges ones with the nonmetals, I have found those to be more confusing. So you're welcome to try to use them, but that is not a requirement to finish this lab. And the last thing before we get started on some of my directions are that there are something called polyatomic ions in this lab. And just like it sounds, a polyatomic ion is a ion, which is a charged particle that has many atoms in it. We're going to be working more with those in Chapter 6, including their naming and their charges. But you should be able to start to get the idea in this lab, and I'll give you some examples in this little introduction. The other thing that we haven't talked about yet in Chapter 11 are the transition metal cations. They can't be predicted using the octet rule like we were learning in Chapter 11. Instead, they are more memorized. And as well as that, some elements like copper and iron can actually have more than one cation that are stable. So we'll talk more about that in Chapter 6 as well, but the amount that it's introduced in this lab, you should be able to do it and start getting an idea. So on the first part, ionic compounds, it tells you to make 16 possible combinations of, or 16 possible compounds from the ions that they give you. So how you do that is you take all the ions and make a combination out of each one. So I wrote here the different ions that they have. And so what you would do, you would first, this is how I would start, make a compound with potassium and bromine. And then I just go down with I stay with potassium. I would go to oxygen, and then I would go to nitrate, and then I would match it with this as phosphate. And here, this nitrate and phosphate, these are the polyatomic ions that I was talking about. Nitrate is NO3 minus, and phosphate is PO4 with a charge of 3 minus. And I'm going to give you examples on the next page, but those are the two polyatomic ions. And then after you do that, that would be a set that would give you 4 different compounds. So then I would just go to copper, and then I would just start with the anions. So I would go copper to bromine, then copper to oxygen, then copper to nitrate, then copper to phosphate. And then now you'd have a total of 8 combinations. And so on. So then you would take and go down to the copper 2, and you'd go to bromine, to oxygen, to nitrate, to phosphate. Now you'd have 12 combinations, and for the last to get the 16, then you could come down to aluminum, and you'd go to bromine, do the combination with oxygen, with nitrate, and with phosphate. So when you're done, you would have 16 different compounds that you've written the formula for. I also, before we move to the next page, just to mention to you on the previous page, I talked about how some metals can have more than one ion, like the copper. So the example here, there's a copper with a cation with a +1 charge and a copper cation with a +2 charge. These you treat just like you would treat cations we've treated before. The big difference here is in the naming. So because copper can have 2 charges, we write using a Roman numeral what the charge would be. So that we would distinguish between a copper with a 1+ with a a Roman numeral 1, and a copper with a 2+ with a Roman numeral 2. So let me do a couple examples for you on the data page to show you what they would want, how it would look like. So the whole idea in this is I just showed you with puzzle pieces first. So to make potassium with a phosphate ion, so here is phosphate, this is a polyatomic ion. So we have a K plus and a PO4, 3 minus. And so if you look at it and think about it this way, when we were putting compounds together, we were just looking at the charges. So for a minute, just don't imagine that there's phosphate here. Just don't imagine the PO4. If we were figuring out how many potassium we would need to go with this phosphate, we could look at the charges. So to figure out how many potassium, we'd look up here and we'd say, oh, that has a -3 charge, so it's going to take 3 potassium. So it would take 3 potassium, and then to figure out this phosphate, how many phosphates we would need, we would come back up here, and potassium has a +1 charge, so we would only need 1 phosphate. And so we would just write the PO4. The phosphate, the polyatomic ions will stick together, and so the P, the O, and the 4 won't separate, or their numbers won't change. And naming this is quite simple. You just name the ion potassium, and then polyatomic ions have their own names, so this is potassium phosphate. Now you can see with the puzzle pieces, and this is why for some people they'll help you, you have to fit them together so they make a block. And you can see to fit these two together, we would have to put 3 potassium with 1 phosphate. So it just gives you a visual of how many you need of each to make it fit together. Now this copper I chose because just to really show you about the naming. So you have copper 2+, and then the bromide ion. Like we were thinking about, to figure out how many coppers I would need to make this compound, you can look at the charge over here on the bromine, and the bromide is only a 1, so I would only need 1 copper. And then how many bromides, you could look at the charge on the copper, and then we would need 2 bromide ions. Now the difference here comes is because copper can be a 1 or a 2, so when I name it, I have to tell you that it's a 2. So it's copper 2 and then bromide. So just let me point out that the 2 here is not because I'm using 2 coppers, but because the charge of copper is 2. And here's the puzzle pieces again, and really they're just to show you that to put this compound together, it would take 1 copper to balance with 2 bromides. Whoops. Because remember, what we're trying to do is make sure when we add the charges together that they equal 0. So this is what your data piece looks like, your data page, and I've selected 4 of them, and I'm not going to do them in any order. It's more random just to give you an idea of the different examples. So you could put them in any order you want. The order you put your 16 does not matter. So let me just start with an example. Let's say I started with potassium and bromide. So you'll just write the 2 pieces that you're using. And then the ion names, remember the positive ions are the same as the element name. And the negative ions, you change the ending to IDE. Now the number of ions required is how many you would need, and this is where you can look at the opposite charge. So for potassium, I could look at bromide, and it has a 1 here, so I would only need a 1. And then, let me back up, because before I get going on that, remember the first thing I should look at, let me erase that, sorry. The first thing I should look at is when the charges are the same, remember you always only need 1 of each. So that's that would be a 1 and a 1. So that just says how many you need. And then you write the formula together. So I need one of each. That's just the formula. And then the name is potassium bromide. Okay, so let's try another one. Let's try, and remember I'm skipping around just to show you different examples. So there's, let's say I did copper and oxide. So the ion name, now in copper, in the ones that you have copper, you need to remember to put the Roman numeral, because you'll either have a copper 1 or a copper 2, and the charges are based on the Roman numeral is based on the charge. And then the oxide ion, remember the negative ions, you change the ending to IDE. So how many ions are required? Again, when we look, if they both have the same number, so a 2 plus and a 2 minus would cancel each other out right away. So we would have one of each. And so the compound formula would just be CuO. And we would name it copper 2, because that's the name of the anion, and then oxide. So let me try two examples with polyatomic ions to let you see how that would be. First, let's try aluminum with the nitrate. It's NO3 minus. So their names, aluminum and then nitrate. Oops. Remember, polyatomic ions have their own names, and we'll talk about more in Chapter 6. And then the number of ions required. In this case, we check it out. The ion charges are not the same. Even on polyatomic ions, if the charges are the same, like they both have a 3, then you would cancel it out, and it would have one of each. My dog's playing with her toy. And so you'd have one of each. But in this case, you have a 3 and a 1. So we can use the crossover. So for aluminum, I would look here, and there's a 1 charge over here. So I just need 1 aluminum. The nitrate, I would look at the aluminum, and there's a 3. So I'd need 3 nitrates. So the formula, I would need 1 aluminum. And in polyatomic ions, when you need more than 1, whoops, I drew my parentheses too quickly, you need to put it inside a parentheses. Otherwise, if I went ALNO33, it would look like I had 33 oxygens. So this would be incorrect. So if you need more than one polyatomic ion, use a parentheses. And then you would just name it by naming the positive ion followed by the negative ion. And then let's do one where we have more than one cation. So what else did I have? Oh, let's do copper plus. And let's do it with phosphate. So the copper, remember, in the copper and the naming, the only thing you need to remember is if it has a 1 charge, you'll put a 1 behind it. If it has a 2 charge, you'll put a 2. And then this is phosphate. Now the number of ions, you can again check the charges. If they're the same, you would only need 1 of each, even with polyatomic ions. But this one's not the same, so to figure out copper, I'd look over here, and phosphate has 3, so I would need 3. And then for phosphate, I look here, and copper has 1, so I just need 1. So then I just wrote down I need 3 coppers and 1 phosphate. Notice when you write the formula, the charges aren't written because they're canceling. And then to name it, you just write the name of the cation, copper 1, followed by the anion, phosphate. So hopefully that gives you enough to start on ionic compounds, and if you have questions, you can send me an email. So let's look at the covalent bonding on the second part of this. And a big part of this lab is understanding that for a lot of the representative elements, we can actually predict the number of bonds and lone pairs based on their location on the periodic table. So we're talking about non-metals when we talk about covalent bonding. So in general, we would have 4A, 5A, 6A, or 7A. So the valence electrons we can tell by the group number. And this is the kind of cool part. For a lot of times we can predict the number of bonds based on the octet rule that says that each atom would want to have 8 electrons total. That, remember, is so it can have the stable electron configuration of a noble gas. So if carbon, or sorry, I was just thinking of carbon because it's in group 4A. Group 4A, like carbon, has 4 valence electrons already. So if I say 8 minus the number of valence electrons, then it tells me how many bonds it would like. So carbon, I would predict, would like 4 bonds, which it actually does really like to have 4 bonds. Now going down, for example, in group 5A, they have 5 valence electrons like nitrogen. So if I say 8 minus 5, I predict that nitrogen or other elements in group 5A would like 3 valence electrons. And then oxygen, for example, is in group 6A, so 8 minus 6, we would predict 2 bonds. And the halogens in group 7A, we would predict 1 bond. Well, with these bonds, sometimes you have to have lone pairs, remember from the lesson? Because when you look at the element, except for hydrogen, we want to have 8 electrons or 4 pairs around it. So if I already have 4 bonds, then I would not need any lone pairs. If I had 3 bonds, that only represents 6 electrons. So I would need 1 lone pair in order to have 8 electrons around it. The pattern here is your number of bonds plus your number of lone pairs would equal 4. So if I had 2 bonds, which represents 4 electrons, I would need 2 more lone pairs in order to have 8. And if I had 1 bond, I would need a total of 3 lone pairs. So in your book, the covalent bonding, they really use this idea to help you draw the Lewis structures. So I've drawn the different puzzles, and part of the reason is because the skeletal structure is kind of hard. Now CH4, the ones I think you might have trouble with, I'm going to set up the skeletal structure for you. So this example, whoops, I'm not going to draw all the bonds for you. So you would have carbon in the middle here at the front, and then you have the 2 hydrogens and the bromine and the chlorine around it. In this example, remember hydrogen can't be in the middle, so you have the 2 hydrogens connected to each, 2 carbons in the middle, and then each carbon has a hydrogen. So remember, the hydrogens aren't going to be attached. You're going to attach the carbons to each other, and then the hydrogens to each carbon. And then the next example is very similar, except it's going to have a hydrogen and a chlorine attached to each carbon. Oops, sorry. And this guy is very similar. Now, in these, I want you to think about, especially with carbon, it likes to have 4 bonds. Hydrogen, remember always, hydrogen only has a single bond. I'm writing it big in here. That kind of helps you. On these with carbons, you can probably go through and figure out how many bonds each carbon has, knowing that carbon has 4 valence electrons and it would like 4 bonds. On this one, the structure looks like this. And the hydrogens are attached to, the 3 hydrogens are attached to the carbon. Then you'll attach the carbon to the oxygen and to the hydrogen. HCN looks like this. And this guy looks like that. So you'll have the carbon is attached to the hydrogen, and then the carbon is also attached to 2 oxygen, and then the hydrogen on the far end is attached to the oxygen. So there's no rings or anything like that. Now, in class, when we're taking the test, I know probably you're thinking, oh, how do I know all this? I would either set it up just like I have here for you, or this would not be the kind of question that we'd have to look at. But it's worth thinking about. And remember, in general, carbon likes to have 4 bonds. Oxygen with 6 valence electrons likes to have 2 bonds. And hydrogen will always only have a single bond. So what you do now, I've given you the skeletal structures. You try to finish the Lewis structures. So I want to do the same here. I feel like you should get this one. But I'm going to draw the skeletal structures for you. Remember, there's no ring, so when I draw hydrogen next to it, that hydrogen's going to be connected to the nitrogens in this case. Now, nitrogen has 5 valence electrons. It's in group 5. So from what we were talking about on the previous page, if you want to get up to 8, you're going to have 3 bonds. So we would predict things in group 5A would have 3 bonds. Remember, hydrogen really only needs 1 bond. I think you can do that one because phosphorus is in the middle. And then oxygen, okay, I think you can do water. This guy looks like it's kind of crazy. Oops, I keep trying to draw the bonds, but I want you to practice drawing the bonds. So, remember, hydrogen's going to have a single bond to the atom it's next to. In this case, the one carbon will be attached to an oxygen, and then oxygen's kind of in the middle, and then the other carbon's on the other side. Let's see, just 2 oxygens. And here's sulfur's in the middle. You probably could have done that. So on this one, remember, this is about group 6A, and in group 6A, they have 6 valence electrons. So when you have 6 valence electrons, to get up to 8, we would predict that you would form 2 bonds. So think about it. Hydrogen forms single bonds. Carbon with 4 valence electrons, we would predict 4 bonds. Oxygen would like 2 bonds. And then things like sulfur would also like 2 bonds. Oh, a halogen like chlorine only has 7 valence electrons, so it would like 1 bond. Now the big thing here is, remember, the total number of valence electrons matter. So make sure you're using all your valence electrons and giving everybody an octet. So I was going to set up for you on this page as well, just to set up, but this is on the reflective exercises. And I was going to set up some of the skeletal structures because they can be challenging. This one I erased. I made my picture too big, but it has 2 carbons and then 4 chlorines, which means there's 2 chlorines on each carbon. Now remember, don't forget the total number, total valence electrons. You've got to use all of those electrons, and you want to be sure everybody has an octet except hydrogen. Okay, here's carbons in the middle, and it has 2 hydrogens around it and 2 bromines around it. And here, you can do that one. Phosphorus is in the middle. And here we have carbon with 2 hydrogens, and then it has a nitrogen which has 1 hydrogen. Okay, so again, before I finish on the covalent compounds, count your valence electrons and use them all. And then the second thing is, remember the octet rule. Everybody has 8 except 8 electrons except, and hopefully you're saying it to yourself right now, hydrogen. Okay, please feel free to send me an email if you have any questions, and just remember this is practice to help you with ionic and covalent bonding.